Okay, let's start our first meetup about Tarantul database management system. So today, Sergey and Alexander will share about Tarantul, about Tarantul features and how it can be applied to speed up applications. So I think Sergey will start, please.
Actually, I'm going to start. Yeah, thank you, Yuri. Thank you for joining us. It's a big pleasure to present, to run this webinar and present our point of view, our approach, and our product. My name is Alexander. I am key account executive, and from our side we also have Sergey Harlamov is our chief solution architect. Both of us are working in VK. VK is one of the biggest Russian internet companies. And actually, both of us, myself and Sergey, working in B2B segment and responsible for a solution named Tarantul. This webinar powered together with our partner in Japan named Intelix. And in order to expand what Yuri said, we are going not talking only about Tarantul or in-memory database. We are going to describe a bit more about distributed in-memory systems. And of course, we are going to focus on our main product named Tarantul. So let's start. Let's start from brief agenda. Myself is going to run kind of general introduction, and after that, I'm going to pass the word to Sergey, and he will give the brief introduction about distributed systems in general, and also he's going to cover main cases that we're working on and we're facing, then we're working with enterprise level customers. First of all, let's talk a bit and define a bit business and IT justifications and expectations when we're talking about in-memory solutions and in general about current situation in IT. So as you may see, this research based on Deloitte from the past year, and you may see that there are different types of development goals that right now different types of development teams or companies are faced with. So actually, the main goals of these teams are to produce services, to make it fast, make it robust, to make it quickly, and actually together with that, the general idea is to move, for example, from monoliths to microservice models, microservice architecture. So actually, these are major priorities that right now face different type of organizations. Then they're talking about digital transformation or whatever. At the same time, when we're talking about different types of digital transformation, we are facing with system requirements, which is actually focused on high throughput, low response, real time, and etc., etc., etc. From our side, we also run kind of survey. It happened, let's say, 1 quarter ago, and we talked to the biggest 100 biggest IT organizations in our country, and actually you may see the responses from responders on our question. Actually, the main question was if they faced with the different type of tasks related to data integration. What does it mean? And we're not talking about peer-to-peer integration of different systems. We are talking about consolidation of data from different resources in order to have it up to date, have it ready, in order to run services on top of that. And as you may see, most of them are really faced with, and most of them really tried to solve it during the last year. So last year, 1 year ago. If you can have a look on the second question, you can find that most of them were tried to make this data integration based on database application layer, or using the middleware occasion. So based on this slide, or based on this information, we can really make a conclusion that the topic that we're going to talk on is really important for most of the IT organizations. And now let's talk about IT reality and business expectations. From IT point of view, they're still faced with a different, let's say, probably it's not issues, but different type of limitations. Here we're talking about the multiple and quick change of in data quality in data. Here we're talking about the growing of number of consumers, integrations, partners, landscape, etc., etc., etc. We're talking about multiple data sources and so on. And from a business point of view, they still want to run different, run complete applications, complete solutions, and trying to cover different aspects of the business. For example, most of the businesses right now are trying to solve issues with the omni-channel, for example, user experience, or they're trying to work in real time. And of course, most of the businesses across the world are looking forward for quick release and reducing the time to market. Then they're producing solutions. Another aspect of existing IT situation is, let's say, it's most of all came from the historical reasons. And here we're talking about different types of monoliths, monolith architecture, and different type of systems that each of them has their own database. And actually, the consolidation of the data makes kind of troubles if they're trying to implement it. So yeah, we're facing a lot with the introduction of new services, because each and every change should affect entire system, which is really pain point of big enterprise. It's also requires a lot of preparations, planning. The companies need to run change requests, and it takes a lot of time. Also with the monoliths, when we're talking about them, it's the main issue with them is the really limitation when talking about scaling, and then we're talking about costs. We, from our side, believe in memory technology. Of course, we are not alone. There are a lot of different vendors of in-memory technologies, but yeah, we are in this slide. We are in the middle. We named Tarantul, and actually, yeah, with the latest years, the usage of in-memory technology has become significantly cheaper than, let's say, 10 years ago. And it has a low latency, it's predictable, it's robust, and actually there are a lot of business cases that business allow to create based on in-memory technologies. In-memory technologies actually playing a crucial role. Then they're talking about kind of bridge between the business channels, which can be the services or applications, and the core systems that each and every company has. When talking about core systems, it can be ERP, data warehouse, BI, whatever. Yeah, and actually, each and every change in this core system it's hard to implement, and it's cost effective and time effective. And at the same time, as it's already was said, the business want to make a lot of changes and deliver new channels for business communications. Here we're talking about the web applications, mobile applications, and etc., etc. And actually, one of the crucial roles of solutions like Tarantul is to place in middleware between the business channels and core systems and provide this type of bridge between business expectations and IT reality. And here again, we're talking about time to market, which is lower than if we're going to implement any changes or any updates or any new features on the core systems, on the level of core systems. So actually, that was the introduction. And here I give the word to Sergey, and he will take you through the distributed in-memory systems and in our cases. Sergey, please.
Hello again, everyone. Thank you for taking me here. Some image check. Do you see the image after transition?
Yes, yes.
Please confirm. All right. So after this, so business introduction, let's talk a bit about the technical side of this problem. Let's talk about distributed world of distributed storing and all the adventures and challenges and areas of problems that are not known in the world of relational database management system, right? The conventional database world. And to do so, let's start off from a cozy and comfortable homeland of a single node relational database. Here on our home planet, the air is safe, you know, it's acidic, if you get the joke. Yes, we have all the atomicity, consistency, isolation, and durability guarantees in our database. We tend to organize our data in normal forms. We use all the benefits of normalization. Everything we do in our home database, in our homeland, right? It's safe, and again, transactions can be consistent up to linear serializability, which is again the most safe way you can is the safest way you can get, right? But then something good or bad happens, right? So either you get more customers, or you decide to launch a huge service and new type of service to your clients. For instance, I don't know, say you want a new type of personal cabinet, right, for your users, and you want to serve the data from your monolith. And here you face the grim reality of online transactions that come to your database. First off, you will probably meet the increase in read throughput, right? For instance, let's take the authorization cluster, right? You used to serve all the requests from your single node relational database, and then you maybe you've already had a couple of surges of users before, and you've moved your database from to a bigger machine, right? And now you've come to a situation where that doesn't help. You actually can't buy a bigger server. And then a typical step for database administrators and developer teams in general is to put a replica, right? So you probably what you would do is you put a replica of your database and start to serve your data from a 2-point, where one of them will be write only and others will be read only, right? Sometime soon, your latency requirements may grow with this. And again, at some moment of time, this won't be enough, and you will come to the situation where your request pattern also includes an increased write request. And that's basically when you know you screwed up, because at this point in time, you already have some kind of this situation around. So you have a couple of relational databases storages. So let's say you have replication on this axis and sharding on this axis, right? So you, at this moment of time, you already have some so-called matrix of databases, which is costly in exploitation, which raises a lot of questions in terms of administrations. Now you should always bear in mind how your data is spread over the cluster, how is it sharded, how to ensure locality of data to uphold consistency and consistent transactions on logically connected data, how to make it transparent to developer when you do such things as rebalancing, how would you fail over such constructions. A whole new area of new and complex tasks arise when you move from the comfortable and sweet world of relational databases to the scary and uncertain, I'd say, world of distributed databases. Now you should keep in mind all these problems, and you should first off keep in mind that no matter what technology you're actually using, no matter what distributed technology you're using, you should keep in mind that you should now you're in a situation where you have to choose one, right? Consistency or availability. According to the CAP theorem, you've got to choose one in the situation where you don't want to end up having a split brain in your cluster, right? So you don't want to sacrifice partition tolerance of your cluster. If you think about it, so first of all, yes, when you have all those questions and you, for instance, take yourself in a seat of a database architect, you would have to come up with, for instance, such access as I introduced before, like sharding and replication access, right? You will have to organize your storage somehow. And secondly, you will have to somehow solve the task of routing the requests for your storage. So it's either you should have a very smart client, a very in Russian the set expression is fat client, right? So the client which is very smart, but that knows the map of the cluster, for instance, that will handle balancing and failover in such situations. This closely reminds the situation as it was solved by solutions like Redis Sentinel, for instance. Another thing you could do is to create another type of nodes. So you would have a storage node and you will have a router node, a node that is stateless, that doesn't store state, right? And would take all the tasks that are connected with routing actual requests, with the failover, with the updating and synchronization of cluster map as it changes, right? As you decide to pour into several new nodes, or you would like to, I don't know, rebalance the cluster in case you need so. In such situation, you still have ACID guarantees, and or I'd say you may still have ACID guarantees if you are using right technology, and you can get safe transactions within a single node. Here you still have all the guarantees that generally comes in a relational database storage. And in terms of cluster, you will have to come up with all kinds of hints and tricks to manage, monitor, and generally keep the cluster healthy, no matter what, no matter network disconnections, dead servers, I don't know, power outages, and etc., etc., etc. So your cluster should be able to emerge through all those these misfortunes throughout its way. The benefits, so as you probably could have guessed by now, Tarantul solves as an in-memory, as a member of in-memory family solutions. It solves the distributed problems in a similar manner. So we typically have a set of storage nodes that are divided by replica sets, right? So we have a master storage and replica storage in the most simple of scenarios, and we have an amount of routers that linearly scale the request from client coming to our cluster. Thus, we and keep in mind that if we are using in-memory storing for actual storage of our data, we get predictable and generally low latency. As we are using distributed cluster, the load is distributed by the nodes, and we have low cost, high availability. So we split the throughput, we split the load, and if you are using right technology for routing, you generally get a transparent and smart scaling. What I mean by transparent is that the developer of applications, the developer of business logic actually shouldn't think about where the data, on which actual physical node your data is. You should count some affinity key, right? And then the application itself or routers will come up with the right node to route to that request, right? As a kind of drawback, you got the complexity. So of course, such systems would be more complex than a single node database, right? Because there's, as we've discussed before, there's so many new type of problems that arise there. And a second possible drawback is that when you move from a cozy and simple world of relational databases, another thing you could miss is the key value interface. Well, it's 2022 by now, so people actually got used to key value interface with thanks to Redis, Mongo, Couchbase, CouchDB, and other technologies. But still, of course, SQL is a much more mature way of interacting with storages, right? Some people may miss it, especially if a lot of procedures are at stake, right, in the system, and some are written in such esoteric languages as PL, PGSQL, if you allow me such term for this. Okay, by now you could have some questions. Let me see and check the chat if we have some. No, we are clear. If any questions arise here or comments, please feel free to drop them in the chat. I will come back to them later. Chat is open and I can see this. Moving next, let's see and actually sum up all the differences we have between typically single instance relational database systems versus distributed in-memory systems. And let's judge them according to three main areas, namely performance, fault tolerance, and reliability. First of all, what can be said in terms of performance? Of course, there is a difference. First of all, distributed systems are more performant by default because they're like numerous machines there. So you typically can get a better performance and moreover get it linearly. While relational databases are limited by vertical scaling only. For relational database, typically disk access is also a thing. Right, you are limited by the input-output operations throughput your disks can go. While with memory, the access speed is much more and orders of magnitude faster. How about syncing state between the routers? Oh, sorry, excuse me for that. I got a question in chat, and I think I will pause on that and actually get into description about that. So the question is, for those who don't see the chat, how about syncing state between the routers? Should it be a tricky task? well, routers actually are stateless, so you shouldn't sync them. So okay, let me tell you about this in terms of Tarantul. In terms of Tarantul, you shouldn't actually sync routers, because in Tarantul, you kind of get full mesh topology in the network. So all routers are connected to all the nodes in the cluster, and or you got an etcd as a third leg for that cluster. So you can use it is called a coordinator for your cluster. So you can use a third entity for your cluster to hold the state also, who's master and who's replica, right? So it is, to sum up everything I have said, you should either have a cluster coordinator, external cluster coordinator. This is usually done with the help of etcd, three-leg etcd, right? So etcd deployed in a three separate environments. Right, and routers can use this external provider and exchange with each other through this external coordinator, right? It is option one, and it's generally the best practice solution, because it is able to withdraw significant network storms. So, right, the situations when you cut off lines, the three legs of this etcd kind of prove that you won't have problems in such a way. While with there is also another way to do so. If you're planning to build actual storage, your routers can have an UDP health checks with all the cluster, and each router can individually know and build and actually build and update this cluster map by itself, while actual requests can be balanced between routers. So requests of client can actually fall on different routers, and client will actually don't care about which one it would be, right? So I hope I answered that. If you have further questions, please write them in chat, and we can come back to this by the end of my presentation. All right, so let's keep going with performance. Another peculiar thing about in-memory technologies, distributed technologies, where they win, is that they typically use more efficient binary protocols, and they don't inquire a complex SQL statements parsing, right? So we all do understand that parsing of SQL statement, the building of this request, the map, etc., this is kind of a complex task that also influences the latency of request. While with key value, when we have indexes, it is basically an index lookup and a fetch of a data. It is much more simple, right, with key values. As of fault tolerance, it is quite simple. If you're using single instance of relational database, we get quite obviously enough. We got a single point of failure. We generally tend to solve this with active passive solutions, but they still would lose to in-memory, because if we will think in terms of recovery time objective and recovery point objective, we would still generally tend to have better numbers with in memory storages, because of disk overhead on this in every operation involved. We can have in distributed systems, which as a drawback, we should think about failover and how is it realized. If we take Tarantul as example, in Tarantul, failover is actually mechanics of failover. I have just described mechanics of failover when talking about synchronization of routers. So if we see if a master is dead, one of the routers well, see the situation, they then either talk it through with each other, and based on the gossip protocol, they then say, okay, now we have a new master, and then it's set, or it is done again with the help of external coordinator. When router sees that the old storage is down, it marks up there, then nodes vote to choose the next replica, and a new replica becomes the master. The process actually is not that complicated. In terms of reliability, well, again, with a single node, in terms of recovery time, you have the time you need to replay your previous backup, and the recovery point is the last backup in the worst case, right? With when we have master slave configuration or active passive configuration, we have 0 recovery point, and the time is the switching time. With the in-memory systems and distributed in-memory systems, it is generally the same. However, it is much easier to build a geo-reserved clusters, so where the replication log is actually the 3, well, it's actually ping, right? It's 1, 2, it's actually 3 pings between the server. And you have in some kind of in-memory technologies, for instance, so, well, in most of them, we have some kind of write append, so, well, write ahead log, right? Not append only file, right? Write ahead log, which is the persistent store of each transaction that happened on this particular node. This log can be used in order to know, it can be used after some crashes and breaks. It can be used to restore state and to replay the state after the last snapshot, right? So in terms of node failure in Tarantul, for instance, right, the situation when our master dies, when later this node will be up again, it will start up with asking router what it is. It will find up its it will find up its local replica ID. It will join the cluster saying this, I have this ID. It will then get its place in the cluster, connect to the shared one, and get all the data it needs, which includes the changes to the data that happened after the last file in that log. Sorry about that. Okay, by now we actually just have, well, quite deeply dived into the problematics of distributed systems, and now let's see the major use cases of distributed memory systems and typical architectures. Let's start off with typical architectures. As you may see, what is general here? The general idea here is that RAM is still quite expensive resource, so you probably don't want to store all your data in memory. There is still quite a need for relational databases, and they're still good for a number of reasons, right? But so we are generally speaking about scenarios of cold and hot data, where we build data marts or caches, caches and data marts for data coming from some master source. We may use CDC or change data capture mechanisms to capture the data. We can build simple caches, well, transactional caches, right? That work with time to leave and eviction of data. We can actually build and use in-memory grids now for using it as a main storage as well. We can plan, for instance, for heavy authorization services, right? For the storing of tokens, sessions, etc. We may choose to use a distributed database from day one because we with authorization, right, we don't know where's the limit of users. We always may grow, always there may be a situation where there is more services and more people or more products using our authorization, right? Let's talk about more particular use cases. So first and one of the most popular ideas to use distributed memory storage is client profiles. And why so? Because client profiles is a type of data that is both changing very fast, so the storage should be able to sustain a heavy write access, right? Write request. And at the same time, it is heavily read. It's read by from personal cabinets. It's read by promotions, loyalty processing services, real-time marketing services, etc., etc., etc. And it deals with it's kind of a data that is usually and typically queried by queried in real time. The problem businesses, or for instance, so at least what we have seen, the problem with such a task is that despite the fact that we may have several disconnected product teams with their own storages of their profiles, we don't have this single view. We don't have a single place where we can query all this data, for instance, for the needs of load processing or real-time marketing. And there is no way to do so. So if we remember the slide that Alexander showed us later with this middleware services, right? This is a perfect example of such a middleware service, a data mart that will then be used by several domains, by microservices and maybe macroservices or monoliths of other domains and will be later used by several services. So the idea here is that we use Tarantul or any other distributed in-memory technology to build this middleware solution that utilizes CDC or streaming. So, for instance, we can get the deltas from Kafka or MQ. Or change data capture mechanisms where we parse logs of existing database, or just I don't know, use HTTP and as a channel for some events. We can then implement data mart storing basic customer data, some maybe windows of change, for instance, some data that can be calculated on a window of, for instance, an average spending of a client, right, on the event stream of transactions. We can then both keep this data in the actual state, right? Keep it actual, and serve a huge amount of read throughput load through this. And why we can do so? Because as we discussed later, we can scale horizontally where imagination is the limit. have seen plenty of systems to redeveloping it again and again. There is a comment here in the discussion group that such client profiles is a common, well, there's a doubt that it is a kind of a common task. It actually is a common task, especially when we talk about such projects as, well, demolition of CRM monolith, or we discussed when we renovate billing subsystems, and we need, well, we need this client profile for services of several domains. So it actually works like this in such scenarios where a monoliths are deconstructed. And another example where this pattern is actually used and helpful is where, for instance, we have a retailer in Russia, X5, that is very agile. So they're digital they were digital from day one, but they had several commands and separate organizations. So yes, they have like 20 or 30 services and products, but they are completely isolated from each other, and each of them have their own authorization. Each of them has their own client profiles, and this comes as a problem when you're talking about omni-channel marketing, when you talk about single authorization for your commands. And on a certain scale, such tasks becomes actually prioritized. So, and we have seen a number of such data marts that host several tens of thousands of requests per second and store tens of millions of over 10 million users in such a database. It is a retail example, and there's even more monstrous numbers when we talk telecom industry. There is another interesting and peculiar, I hope I answered the question right. So there is another interesting case, which is a retail stock cache, a retail stock data mart, where we had to build an express delivery service within 2 or 3 months. Well, actually the first pilot was even faster than 2 months. So what is the idea and what is the problem? I'm not sure is the applications for food delivery, so how such applications are popular in Japan. So do you have a lot of such applications? You can comment, or Yuri, maybe you will answer.
Yes, actually, I've seen many applications like this because there are plenty e-commerce companies in Japan and of course around the world, but particularly in Japan, for example, there are large companies who need to.
And do you deliver products like in 15 or 30 minutes? So fast delivery. Like I want a cola, and I go to app, I order cola, bread, and fast delivery, very fast. Like in 15 minutes, it will be at home.
This is this is really good questions. I know that, for example, fast retailing company, which you probably know as Uniqlo.
Uniqlo, right?
Yeah, you know that probably they like to automate processes as much as they can, so they have a lot of automation right now on the endpoints of retailing, and probably they working on this, how to update what we're basically keeping on storage and what we can sell right now in real time. But still, I believe there are a lot of work for businesses to do, because I like a customer, for example, in Japan, I can't feel that this happens like fast, real time. I don't.
This is actually very cool, because that telling people about something that is not quite mainstream in that region is it feels great actually. So let me maybe paint the situation in a brighter colors. So we have an aggregator services, right? So we have like a taxi service like Uber, right? We have several of them, like Delivery Club, Yandex Go. There are several services which offer a delivery from restaurants. The idea is that you have a catalog of restaurants. The application tracks your location and it knows which restaurants are close to you. You then go to app, choose a restaurant, see from a menu, pick your, I don't know, double cheeseburger, cola, etc., etc. Make that order, and they will deliver it to you in 30 to 40 minutes. It's their claim, right? This type of services have worked in Russia for like 3 or 4 years already. I don't even remember when it started. Quite long time ago, but it they didn't deal with actual grocery stores, and you couldn't order food from that. This was true until the pandemic happened, and the first. So this was idea, and it actually so retailers got dollars and dollar signs in their eyes, so people are sitting at home, they do want products. So what to do with that? We need to bring products to people who are locked up at home. What's the trick here? The trick here is that the retail store and retail management system, they don't know the actual stock of their milk, bread, etc. On the moment in time. The only moment in time when they know for sure in a centralized database what they store in each store, and they have like 20,000 of stores, 20,000 of stores with 50,000 of positions in each. So think about it, 20,000 shops, 50 positions in each. This stock is updated in central database only once per day, and you don't actually have an actual stock for the shop you want to eat in. This breeds the problem for the user. I want to buy a cola, and maybe take example where I only want to buy a can of cola. I place that order. I pay money from Apple Pay. Okay, I got no money on my account for that cola. Courier, or what is the right word for it? So I forgot the right word for that. Courier is a French, so the guy who actually delivers, right? So deliverer comes to the shop, and they are out of stock. They don't have a cola. I see my order has been refused, and I become angry and never use this app again. This is the typical scenario, and this is a huge problem. We will call this problem the basket completeness. So, and this can be measured in percentage, where we say, so we can complete the 99% of baskets to every customer. So, and this can be true only when we don't screw up the stocks, right? And we always get the right stocks to people. So what we know that we don't know as does anybody know where actual stocks? Actually, yes. So you have 20,000 of shops, and each shop, of course, tracks the remainings, right? The balances of the products on stock. But we have 2,000 of them, and we want to be able to serve this catalog from the shops real time with like 2,000 to 5,000 requests per second at least, and we should be able to scale this system for 20,000 of shops we get. This is the trick here. Let's look so let's look about closer to the solution. And I remind you that we launched this like in 2 months, and it was a huge win for all the parties involved. So we have aggregator services, right? We have these apps people come to actually place an order. It is the two external to the retailer the project actually happened in, and one internal delivery service. So Magnet This is the name of retailer. This is the internal magnet delivery, and this is external deliveries. What we did was we've deployed a parental data mart, so distributed data mart, for two types of objects. So catalog and balances. Catalog, we would update the catalog once per day from the centralized master data storages. We would load article names, photos, descriptions, etc., etc., etc. So we load the how do you call it? Also product cart, right? And then we so now we can have the catalog and serve it to our users. Then we should have to make a small gRPC server, which would take the requests from all the shops. Once in 5 minutes via gRPC API, the shops will push all the catalog, all the current balances it have, and we will work with this load. And this currently works in production for more than 10,000 shops in Russia. So such a data mart hosts the services and allows to get stocks and catalogs for any shop in Russia, powering this express delivery. You may have some questions here. Time due to lack of stock. Yeah, so some of participants actually mentioned the case with Uber Eats where they failed to get this basket. So you're actually familiar with this problem. I'm not sure with the current this current percentage, right? So with current KPI, but I'm pretty convinced that it is higher than 90%. What we've managed to get with marketing. It is cool case, cool because here you have real-time load from actual people using their apps. Here you have massive load from thousands of stores that will load you either whole stocks or data changes. There will be load no matter what. And it has also good case because there's not much you can do about it. There's no much other choices you have, because routing this load, so updating balances in retail management system would be bad, because it is a huge load that comes to RMS that is typically generally already heavily loaded. Other solution would be to route this load to the shops themselves, and yet again even worse solution, because servers and shops are not suited for that. Okay. All right, I've summed up the case quite enough and don't see any questions raising, so let's go on. The last but not least case for today is the case of golden record. Golden record, I guess you're familiar with the term, but for those who are not, golden record is an idea of a master data cross-reference storage, right, or object. So let's imagine a situation from a previous case where we got or a slightly bit different situation where, for instance, we have a bank and we have several domain systems that work with customers, and in each of them customer may have may slightly differ from each other. Different options of names, different telephone numbers, duplicates, and etc., etc., etc. So what if we want to get a unified view of our client? We want to do away with duplicating records. We want to have a service which can serve a cross-reference. For instance, we have our global user ID. Let's call it MDM ID, or let's call it golden record ID. Okay, and we have identifiers that are somehow connected with passport number, with ID in system 1, ID in system 1, and ID in system Z, etc., etc. We want to have a service which can where we could come with a request and say, give me a user profile based on his ID in some subsystem, or based on his passport number, based on MDM. Right? We want to be able to resolve such cross references. This is a non-trivial task because when you try to solve it in a distributed world, you come across the situation where when you sectionize that data, right, when you shard data, you have to choose affinity key. You have to choose a key according to which you will distribute your data. And as we remember from earlier discussion, keep in mind that you have guarantees of the transactions, and you have ACID only within a single node. So in order to be able to update this data, we will have to have sharded storage for the golden record itself, right? For the table like MDM ID, passport number, system ID, etc. It will be sharded by MDM ID, and it will be able to very fastly serve requests. So give me a user data based on MDM ID. But as we discussed earlier, to the same system, you should be able to resolve reverse requests, like give me an MDM ID based on identifier in system. So in order to update this golden record, we will have to do so. And to this, we would need a separate cross-reference cluster. So we will have, in our cluster, we will have actually two separate clusters, one for golden records and one for cross-references, which we will have to idempotently update when we update our golden record. It will be realized via similar mechanisms. So for primary records that may create new golden record or may update existing golden record, we use event-based communication. We either use streams, Kafka streaming, or we use CDC. These records then come to distributed in-memory data storage, where we have a Lua procedure that works near the data and idempotently updates cross references and master data. And on the level above it, we have a microservices that query this golden record for use in, again, loyalty processing, analytics, real-time marketing, and others. I guess I have completed and covered everything I wanted to talk about, and I even have some time left. Thank you for your attention. Thank you for questions and comments, and we would be glad if you join our Tarantul discussion group in Telegram. Please also feel free to use Tarantul.io to know more about how you can use distributed technologies to either boost your performance, build distributed storages for authorization and other use cases where it may serve well. And keep in the loop. In further topics, we may discuss other patterns that are commonly used today. For instance, complex event processing that is also very that is solved quite well using distributed technologies and distributed and memory technologies, namely. So thank you, everyone. Let's keep in the loop.
Yeah, thank you, Sergey, for your presentation. What from my side, I can make a comment that in my professional life, I several times developed something called ecosystem. So many companies will like to build user-centric businesses where they are trying to build all systems and services around some kind of user profile. And this is very typical problem when you starting from small amount of customers, when the amount of customers growing, and at some moment, usually from my experience, around like 1 million users, you facing issue. So basically, you have high requirements to data availability and integrity in that identity provider, which is like a core of your ecosystem. But amount of technologies that you can use to keep with integrity high is very limited. And this is always challenging, to develop this ecosystem core. So many companies facing it and they're developing and redeveloping and inventing something new. But yeah, this is interesting approach, and this is interesting what you shared about this. So just what I've seen like many times from my practice. And yeah, about balance on this and keeping like information about leftovers in the storage and what actually exists in storage right now. I think this is also typical issue for any company which works in e-commerce and retail. This is true.
Yeah, I agree. Totally agree with you.
Okay, so let me, in that case, let me stop recording here. And